to ask during the talks. You will put your questions here, and on the working hours, which is supposed to work with all of the people in the conference, you will have your answers. Okay? Thank you.
Come here. So, I want to start with something very important. Okay. Happy birthday. Stay up, here. Happy birthday. Thank you. I don't really believe it was 60, that's what to say. I don't believe it, but I'm willing to tell you. So, as Ali said, there are notes. The notes contain exercises. They also contain appendices with some additional reading, which actually is going to do. Okay, so I'm going to talk about the balanced water method. And let's start at the beginning. The beginning is a very important observation which goes probably all the way back to Gibbs in statistical mechanics. And what Gibbs notice is the following thing, which may look a little bit paradoxical, but in fact it's not. What notice is that in chaotic systems, in chaotic situations, it's sometimes easier Can you hear me now? What Gibbs noticed is that in chaotic situations, it's very often easier to predict the behavior of big collection of initial conditions rather than individual collections. It's easier to predict the behavior of many initial conditions than to predict the behavior of single initial conditions. So this may look a little bit paradoxical. How is it possible that it's easier to predict infinitely many things than it is to predict single things? Is this helping or interfering? What do you think? Perfect? So let me give you an example of this, to show you that in fact you have all seen this principle in one way or another. So here is an example. So imagine that you have a glass of water, and you put a drop of ink inside. So you put some ink. And then you stir the water with a teaspoon. Okay, so the ink starts to spread. And now, here are two different questions. The first question is, suppose you pick one single particle of ink. And I ask you the question, where will this particle of ink, where will it be after 1 minute, after you stir the water? There is no way you will be able to answer this, because the motion is chaotic. On the other hand, if I ask you, what can you tell me about the density of ink, of all the ink particles? What can you tell me about the way that all the ink particles are spread around the glass after 1 minute? It will be very easy for you to predict it. You just go very fast to the constant density. And again, the reason is the same. The reason is that the motion is chaotic. The reason that makes it impossible to predict the behavior of a single ink particle is exactly the reason which makes it very easy to predict the behavior of all ink particles. Here's another example. You take a very big tray and you fill it with, I don't know, sand. You make a heap of sand that looks like this. And then you take the tray and you make this. Okay, you make it jump. Well, there is no way to predict where different grains of sand will go, because they spread around in a very chaotic way. But on the other hand, it's very clear that once you shake the tray of sand, the whole pile of sand will simply become uniform. So again, it's easier to predict the behavior of a large collection of initial values. In this case, the location of different grains of sand. In this case, the location of different ink particles. This is much easier to predict than to predict what happens to single particles, to single initial conditions. This is the principle, this is a very basic principle in statistical mechanics. It's the reason why in Gibson statistical mechanics work with ensembles rather than single initial conditions. Now the transfer operator is exactly this. The transfer operator is the action of a dynamical system on mass densities, on distributions of initial conditions. You have a map that acts on a set, so it takes a point in the set and moves it to another point in the set. You can ask what happens if instead of considering the behavior of single points, you consider the behavior of whole distributions of points, infinitely many points. That is what the transfer operator is doing. And because on the level of distributions of many, many different initial conditions, there is regularity that is not observed on the level of individual initial conditions, the dynamics of the transfer operator in highly chaotic situations is very simple, as we will see. So in a sense, what we're going to discuss in the next several lectures is a collection of technical tools which are used to exactly show this, that for a very chaotic system, when you consider the action not on single points, but on whole ensembles of points, on collections of infinitely many points, which are distributed in some way on the space, the action on these densities is very easy to describe, maybe even converges to exponentially to a limit, as opposed to what happens to individual initial conditions which just wander around the space in a completely chaotic and random and unpredictable way. Okay, so that's what we're going to do in this mini course. But first, let's make this thing a little bit more precise. So let's start with some setup. So let's assume that T is a non-singular, and I will tell you what this means in a minute, non-singular map on a probability space. So I will denote the probability space by X, B, mu. X is a set, curly B is a sigma algebra of sets, and mu is a measure. Non-singular means that a measure of a set is zero if and only if the measure of the preimage of a set is zero. In other words, the map cannot take a set of positive measure and map it onto a set of zero measure and vice versa. Okay, that's what non-singularity means. Now, let's call a mass density something that looks like this. It's a measure, mu sub f, which takes the form f d mu. So the way that I want to think about this is the following. You have a set x, and you have a function f, which is positive and integrable. Okay? So it's something that looks like this. And the measure mu f tells you how much mass sits above a set E. For example, suppose this is a set E. Then mu f of E is going to be the integral on E of f d mu. So if this is a set E, a subset of the space, then the total mass that is located above it is this integral. Okay? So these are mass densities. And the question we're going to ask ourselves and we are going to answer soon, is what happens to this mass density when you apply the map T to every point in the space. The map T acts on points in the space, so it will shift the mass density around, and the question is, what is the formula of the new mass density after one iteration? So let's see what it is. So what happens to mu f after one iteration? Okay, so let's see what is the measure of points, what's the mass of points which ends up at a set E. Okay? I want to find the density after one iteration, so I will ask myself how many points will end up at E. So this is the measure of all points with the property that T of x is inside E. This is mu f of T minus 1E, which I can write like this. So this is a new measure. And you can see that I have this formula. Okay? These are just manipulations with the Radu-Nikodym derivative. There is a small exercise here to show that because we are assuming that the original map is non-singular, that it doesn't send sets of positive measure to sets of zero measure and vice versa, under this assumption, this measure is absolutely continuous with respect to this measure, and therefore the Radu-Nikodym derivative exists. So we can do this as an exercise. So this gives us a formula. So this is the shape of the mass density after one iteration, and this is the definition of the transfer operator. So definition. The transfer operator of a non-singular map. I'm used to writing these as quadruples. This is the probability space, and this is the transformation. So this notation means that this is a map acting on this set, and this is the measure structure on the set. Sigma algebra and the measure. So the transfer operator of a non-singular map T is the operator T hat acting on L1, given by T hat F is d mu F T inverse d mu, where mu F is the mass density F d mu. Okay? So this is the operator which describes the action of the map, not on points, but on mass densities. And what we expect, based on these examples which I started with, is that when a map T is very, very chaotic, the behavior of the iterates of this operator are very predictable. You take a very rugged, strange density, then chaos will tend to straighten things out, and after several iterations of this operator, we will converge to a constant. In a sense, what we're going to do is describe tools for proving that this is the case. But before we do this, I want to replace this definition by another characterization, which is much more convenient for calculations. In fact, nobody uses this formula to work with the transfer operator. People use a different property, which I'm now going to introduce. Okay. proposition. One, T hat of F is characterized, it's the unique L1 element which satisfies the following condition. By the condition, for every phi in L infinity, the integral of phi against T hat F is the integral of phi T against F. So we think of phi as a test function. And the statement is that this function, this L1 function, is the unique L1 function which satisfies this equation for all test functions phi. Second property is that T hat is bounded, linear. Bounded, linear operator. Third property is that T hat is positive. So what does positive mean? It means that if F is non-negative almost everywhere, then T hat F is non-negative almost everywhere. What's the next property? For every phi in L infinity, for every let's call it G. For every G in L infinity and for every F in L1, T hat G composed with T times F is G times T hat F. Notice that we never leave L1 because when you take an L1 function and multiply it by a bounded function, it remains in L1. So that's a formula that we will use. And another formula that we will use, which I will put a small star here, is the following. T hat F composed with T is the conditional expectation of F with respect to the sigma algebra T minus 1B. So if T is invertible, T minus 1 of B is B, but most of the examples, in fact all the examples we are going to consider in these lectures are of non-invertible maps, and then this sigma algebra is smaller. Now, I'm not going to assume that everybody here in this room knows what conditional expectation means in the general continuous case. If you will go to the set of notes that is available online and look at the appendix, there is an appendix on conditional expectations. If you don't know what conditional expectations are, then I would like to recommend that you read it, just to familiarize yourself with this notion. We are not going to use it until the end of the mini course. So if you don't know what it is, don't worry about it. We're not going to use it for some time. Okay, let me show you. I will not prove all these properties, but I would like to prove the first one because it's very, very important. This is in fact the way that we're going to use the transfer operator. We are going to use it through this equation, and then maybe I will show you another proof of another item just to show you how to work with this characterization. Okay, so proof. So let's start with one. So first of all, let's call this equation star. So first of all, why does star hold? Well, because if you take phi times T hat F, the mu, and plug in the definition of the transfer operator, then what you get is this expression. The integral with respect to mu against the Radon-Nikodym derivative that's written like this is the integral against this measure. So this is phi d mu f t minus 1 this is exactly the integral of phi t d mu f, and by the definition of mu f, this is this integral. So you see that the left-hand side equals the right-hand side. Now, there are several passages here that I'm going to mark by exclamation marks, which you should be able to do. You should be able to complete all details. If you don't see immediately how to do it, then start by doing the case when phi is the indicator of a set. And just make sure that you can follow all the definitions to justify all these steps. So start with phis which are indicators of sets, and then move to general L infinity functions. Okay, so this is a proof that this equation holds. But this is not all that we need. We want to show that this equation determines the transfer operator of f. So determines t hat f. So to show this, what we need to do is we need to show that whenever you have two functions, let's say h1 and h2, which satisfy this equation, with h1 and h2 replacing t hat of f, then they are both equal. So suppose hi both satisfy that for every phi in L infinity, the integral of h1, phi times h1, phi, let's call it hi, are both phi t times f, and let's see that they must be equal. So how do we show the two elements in L1 are equal? We show that the L1 norm of the difference is 0. So the L1 norm of the difference is the integral of the absolute value. This is the integral of the sign of this difference times the difference. So what do I mean by this function? The sign of x is plus or minus depending on whether x is positive or negative. Okay? So this is another way of writing the absolute value. And if you think about it, you see that this function, if we call it phi, is a function in L infinity. So this is really phi h1 minus phi h2, which is phi f, phi composed with t f minus phi composed with t f, so it's 0. So this equation characterizes the transfer operator. So from now on, I want you to forget, I don't want you, but you may forget the definition of the transfer operator and just remember this property, which characterizes it. Okay, so let me show you how to use this property to do calculations with the transfer operator. So let's do, for example, let's do positivity. That's number 3. Of positivity. So suppose f is non-negative almost everywhere. I want to show that t hat of f is non-negative almost everywhere. So I must show t hat of f is non-negative almost everywhere. So what I'm going to do is I'm going to integrate t hat f on the set where it's negative. Maybe this is an empty set, that's good for me, but maybe it's not. Okay? So this is the set of all points where t hat of f is negative. Possibly the empty set, but maybe not. This number here, the integral of a negative function, is either negative or it's zero. It's zero if the measure of this set is zero. Okay? So the only thing that I can write is that this is less than or equal to zero. But this is also the indicator of t hat f less than 0 times t hat f. And this is a bounded test function. So I have this equality. And now, suddenly, everything in the integrand is non-negative. This is the indicator of a function, so it's positive or 0. And this, by assumption, is non-negative. So the result must also be bigger than or equal to 0. So now we have a collection of integrals, which are at the same time less than or equal to 0 and bigger than or equal to 0. That means that they are all equal to 0. So the integral is 0. Now, the only way for a strictly negative function to have a 0 integral is if you're integrating on a set of measure 0. So we are done. Okay? So you see that the trick is to choose the test function according to your needs. And that's the way that it works. Okay, let's see an example of a transfer operator. So I would like to leave the other parts of this proposition as an exercise. It's not particularly difficult. And I'd like to show you now an example. Before I do this, are there any questions? So the example that I would like to do is to calculate the transfer operator of the Gauss map. So the Gauss map is this is the interval map T of x equals 1 over x fractional part. Okay? So let's find the transfer operator. So we work with this equation. Okay? For every phi test function in L infinity, whatever the transfer operator is, the integral of phi t at f of x dx is going to be equal to the integral of phi of t of x times f of x dx. Okay, so let me remind you what the Gauss map looks like. So if x is between 1 and 1/2, 1 over x is between 1 and 2, you have to subtract 1. So like this. If x is between 1/3 and 1 over 2, then 1 over x is between 2 and 3, and you have to subtract 2. So it just moves on like this. So the right way to calculate this is to just split the domain. So this is the sum over the integrals from 1 over n plus 1, 1 over n. In fact, I prefer to write it in this form. And here we have 1 over x minus n, f of x dx. Okay? Because on this interval, 1 over x is going to be between n and n plus 1, not including n plus 1. So you have to subtract n when you calculate the fractional part. So this is what you get. Now we are going to change variables. So the change of variables that I'm going to make is y equals 1 over x minus n, which means that x is equal to 1 over y plus n, and dx is equal to minus 1 over y plus n squared. But the orders of the integration flip. So we get y minus f 1 over y plus n, 1 over y plus n squared dy, and I put a minus here. So all in all we get, when we flip the bounds again, because of the minus, we get this formula. Phi y 0 to 1, sum n goes from 1 to infinity, 1 over 1 y plus n squared, f y plus n dy. So the answer is that the transfer operator of the
bounds on the integral are 0 to 1, right?
Did I do something wrong?
Change variables. Why those?
0 to 1, I'm sorry. Yes. 1 to 0. Yes, thank you. Okay, so the answer is this. Now, when you stare at this formula, then you find that what this operator is doing is it takes x, it calculates all the pre-images of x with respect to the Gauss map, and it adds them with weights. Okay? Now, here is the thing that I'm going to say, believe me that it's true. Had we started not with the Lebesgue measure, but with the invariant measure, with the absolutely continuous invariant measure, then these weights would have summed up to 1. Which means that the action of the transfer operator is an averaging action. It takes a function and it averages all its values on the pre-images with some weights. Now, when the measure is invariant, this is exactly what happens, the general fact. When the measure is not invariant, the weights don't sum up to 1. But still, there is enough averaging going on here to regularize things. So when you start with densities which are very, very jagged, they will tend to be more regular. Now, on Tuesday, we will see an inequality that says this in a precise way. But this is a very general principle here. Transfer operators, like Markov operators, are operators which contain a lot of averaging. And it is exactly this averaging that is what you expect because of chaos, because you expect that when you start with a very, very regular density, if the map is very chaotic and you apply it, it will tend to kill the fluctuation. It will tend to regularize. This is exactly what the transfer operator is doing, and you see it through a sort of averaging mechanism. Okay? Now, if you go to the notes, you will see other examples of calculations of transfer operators. Okay. You may want to do that. Any questions on this? Okay. So I remind you that our motivation is to show that if you have a map which is very, very chaotic, then the dynamics tends to regularize mass densities in such a way that they converge to a limit. This is very much in contrast to what happens to individual initial conditions, which just wander around chaotically around the space. They form, they do not converge. Individual orbits do not converge, but orbits of densities, as we will see, in many cases do converge. Now, before we start discussing how to show something like this, let's ask ourselves, what does such a statement give us? Why should we care? So it turns out that many dynamical and stochastic properties are consequences of such convergence. They are consequences of the fact that when you apply the dynamics of a map to mass densities, the mass densities tend to regularize and converge to a constant. So such dynamical applications include the construction of absolutely continuous invariant densities, the proof of mixing, the estimates for the rates of mixing, the curve correlations, proof of the central limit theorem, proof of other more sophisticated probabilistic type of phenomena. But let's start with things which are a little bit simpler. We'll leave the central limit theorem to the end. So what can we learn? From a statement that says that T hat n of f converges in L1 to some limit. Very good. I'm going to tell you what the limit usually is. Usually the limit looks like this. Well, not usually, but in good situations, the limit looks like this. We will see it next lectures. Let's see for the moment what does something like this tell. What does it tell us? So the first statement is that if you have a convergence of this type, then H is an absolutely continuous invariant probability density. So what I mean by this is that the map, the measure mu h, h d mu is T invariant. Okay, let's see why this is the case. So the first statement is that if you have a limit like this, then necessarily h is an eigenfunction of the transfer operator. So this is very easy. I stated without proof, but the proof is an exercise, it's an easy exercise, that the transfer operator is a bounded operator on L1. If it's bounded on L1, it's continuous on L1. So since T is bounded, it's continuous. Whence T hat H, this is T hat, the limit of T hat n f. This is the limit of T hat n plus 1f. This is H again. Okay? Now, I claim that whenever you have an eigenfunction of the eigenvalue 1, it's going to give rise to an invariant measure. Invariant. So it's enough to check that this integral equals the integral of phi. So this is phi t h d mu. This is phi times T hat h mu. This is phi h d mu. So it's the integral of phi with respect to d mu h. Okay? So you see that for every phi in L infinity, the integral of phi t with respect to the measure mu h is equal to the integral of phi with respect to the measure mu h, which is exactly the statement that the measure is invariant. So you can construct absolutely continuous invariant densities by whenever you have a limit of the iterates of the transfer operator. Another corollary is that T is measure preserving if and only if the constant density is an eigenfunction with eigenvalue 1, but this is trivial. It's obvious that if you start with the uniform density and the map is measure preserving, that the density will remain the same, will remain stationary. So there's nothing particularly surprising about this. Now, I claim that this type of convergence also gives you ergodic properties of the absolutely continuous invariant measure. In fact, it gives you mixing. Okay, suppose T is probability preserving and T hat and F converges to the integral of F, the mu, for all in L1, for all F in L1. Then mu is mixing. Why is it mixing? It's mixing because if you look at the integral of phi against ftn, then for every phi1, phi2 in L infinity, the integral of phi1, phi2 tn, this is the integral of T hat n phi1 phi2. So I'm going to write this in a funny way. I'm going to write it like this. T hat the integral of phi1 times phi2 plus T hat n phi1 minus the integral of phi1 times phi2. Okay? I added and subtracted. And now you see that this integral equals the product of the integrals. And what you have here is bounded by the L1 norm of T hat n phi1 minus the integral of phi1, which tends to 0, times the L infinity norm of phi2. This goes to 0. This goes to 0, and therefore this goes to the product of the integrals. So convergence of this type also implies ergodic properties such as mixing. It's not equivalent to mixing, it's actually stronger than mixing. It's equivalent to something called exactness, but I don't want to get into that. Finally, in the last 5 minutes that I have, let me show you why the rate of convergence here implies bounds on the rate of decay of correlations. But before I do this, I want to remind you what yes, I assume that, I'm sorry, I should have said it. I'm assuming that it is probability preserving, and I should have said it, I'm using it through the assumption that H equals 1. Okay, so just a couple of words about what decay of correlations is. First of all, what are correlations? Well, what is called in dynamics correlations is really not correlations. It's what's called in probability theory covariances. So what is a covariance? The covariance of two random variables xy is this number. The expectation of x minus the mean of x times y minus the mean of y. Now, what's behind this expression? So what's behind this is something very, very simple and not at all deep. So when you have two random variables, they will usually not be equal to their mean. Sometimes they will deviate on the positive side, and sometimes they will deviate on the negative side. So sometimes x will be bigger than its mean, and sometimes x will be smaller than its mean. Now, in situations when x and y are weakly correlated, whatever this means, sometimes when x is bigger than its mean, y is bigger than its mean, and sometimes when x is bigger than its mean, y is smaller than its mean. Which means that the integrand here will sometimes be positive when they both move in the same direction, and sometimes it will be negative when they move in opposite directions. And in such situations, when you take the integral over everything, there will be lots of cancellations, and the end result will be small. So this number is designed to be very small when x and y do not tend to deviate in the same direction. On the other hand, if there is some rule that says that usually, like in 90% of the times when x is bigger than its mean, y is also bigger than its mean, and in 90% of the times when x is smaller than its mean, y is smaller than its mean, then the integrand will usually be positive, and then you get a large number. Okay, so that's the idea behind this number. It's just a number that is small if the random variables don't tend to deviate. There is no rule that says that when one deviates in this way, the other one deviates in that way. In such a situation, the number is big in absolute value, and if there is no such rule, it's small. That's one thing I wanted to say. Another thing that I want to say is when you open brackets and use linearity, it all simplifies to this expression, which is what people usually see in text in dynamics. It's just a simplification. Now, the statement that I want to make is really a triviality. It just follows from the calculation that we already did. But it is in some sense the reason why the transfer operator method is so popular. So the rate of convergence of t hat nf minus the integral of f in L1, the rate by which this goes to 0, if it does indeed go to 0, gives an upper bound for certain correlation functions. Gives an upper bound for the rate in the convergence. Now let me do it in the right way. Phi is 0 when phi is in L infinity. In particular, if you can show that this thing goes to 0 exponentially fast, and next lecture we will talk about tools how to do this. If you can show that this quantity tends to 0 exponentially fast, it will automatically imply that covariances of this form also tend to 0 exponentially fast. And this is the way that people prove exponential decay of correlations. They, instead of proving directly that the correlation goes to 0, usually what they do is they study the rates of convergence for the iterates of the transfer operator. Okay, so the plan for the next couple of lectures is to develop tools for proving exponential convergence of expressions such as this. And then we will return to the question of what can you get from such situations, and I will show you a proof of the central limit theorem in situations when you have things like this. So thank you very much for your time.